All right, what's the difference between kinematics and mechanics? Not a huge difference, but if someone said, I'm studying the kinematics of motion, what would you be doing? Yes? Pretty much mathematical equation and trying to figure out things, aren't you? Mathematically. Galileo was really good at coming up with these equations and figuring out things. Galileo, even though he was a genius, he still had some trouble figuring out why. But why does this happen? And I think that's where Newton comes in. And Newton, just the opposite of Galileo. Newton would have been more of a recluse. He didn't like criticism. He didn't want to publish his work because he was afraid people were going to criticize it. He was a genius. But he was more of a recluse and introvert. Not Galileo. Galileo, very outspoken. He'd speak to 2,000 people at a time. He enjoyed debate, that kind of thing there. So here's Newton, who was actually born on the year Galileo died, so they wouldn't have known each other, but he would have read his work. But Newton, I will say, he was very humble about things too. He wrote a huge amount of stuff on passages in the Bible, and if you ever want to read about him, you'll see he's not very strong Christian. So I would say, though, one statement I remember him more than any is here he is before he's the age of 27. Before 27 years old, he's already developed the laws of motion. He's already developed the science of optics, which has to do with the light, the study of light and lenses and mirrors. And then he also comes up with this thing called universal gravitation equation. It says, I can tell you how any two things in the universe attract each other. If that star is that far away and you got a little speck of dust, the equation will tell you how much attraction there is between those items. The universal gravitational, how did you do that? How do you do that in the 1700s, late 1600s, early 1700s? So, and he was knighted. He was, they understood how important this stuff was. But one of the statements he had, I really enjoyed. He says, if people say, I've seen further than others, if you say I've seen further than others, I mean seen, you know what I mean by seen? Not just with your eyes, but if I've seen further than others, it's because I've stood on the shoulders of giants. And I still remember that statement because he's very humble. He was saying, well, you may say I'm just this, I'm genius, I see things that no other human's ever seen, but I stand on the shoulders of giants, meaning the people that came before me. That's the stuff that I'm standing on their shoulders. That's why I, quote, see further than other people. So he's given credit for all the people before him that had already laid the groundwork. Get that? Yes, he was a genius. He was. Okay, so anyway, let's go on. And if you want to study motion, we're going to start simple, and it gets complicated later, okay? But right now it's simple. The simplest kind of motion I can think of would be linear motion, means it's going in a straight line, and uniform speed. What's that mean? Don't go faster, don't go slower, just go at a constant speed. You get that? Now, if that's the case, we can have the simple equation that they use in middle school. And as a matter of fact, everybody here probably can easily use this equation. Is that correct? So if I take it out of the fractional form, this is how I memorize it. Speed equals like 30 miles per hour. Oh, it's distance over time, isn't it? Okay, now, so I do want you to remember that's distance over time, but I'll take the fractions out. And yesterday I called on people, and you did a great job. You knew that S and T were both directly proportional to D, right? S is directly proportional to D if time is, and you knew how to apply that. I thought you did a good job. And what about S and T? I don't know if that was Jeff. I don't know if that was you or not. Did you do the S and T yesterday?
Let's just say sure.
Yeah, it was you.
Who was it?
It was Liam.
Okay. Anyway, they were inversely proportional, and as long as distance is held constant. So the reason I want you to know that is I don't want you to, I don't know, I had a little trouble sleeping last night, and I started thinking about physics, the class. And I said, I know as I'm teaching this, there's some of you think, That's the equation. Bottom line. Let's go. I got it. That's it. That's all I need to learn. Plug and chug. Plug in the numbers. Chug. I want way more than that. Way more than that. You get that? Now, I'll show you what I mean. I want you to think of motion in terms of a mathematical equation. Number one, true. I do. I want you to be able to plug and chug and get the answer. Let's go number two. I'll show you another page here, okay? I want you to go back here to this page with graphs. Okay. I want you to think of it, we spent time on graphs, didn't we? I want you to see motion in terms of graphs. Okay, so it's way beyond just putting things in an equation. Look at this right here. Now see if you remember this, okay? This shows that as time gets greater, distance gets greater, it's some kind of a direct relationship, isn't it?
Yeah, it's a direct.
And it's a direct proportionality. Now, I thank you very much. I knew you'd remember that, but here's what you probably forgot. In this experiment, was time held constant?
Yes.
No, it kept getting bigger and bigger. Was distance held constant? No, it kept getting big. It kept changing, didn't it?
Slope did.
Right. So is there anything that was held constant? The slope. But wait now, what does the slope equal? And the slope equals whatever's on the y-axis divided by what's on the x-axis. Now, if you did more than just say, I can plug and chug, then you also know that what is the meaning of the slope of this line? What does this graph represent? If you had to see this object, if you saw this object, what would it look like?
Constant something.
And I haven't used that word yet, and I probably wouldn't use it right away since I haven't ever taught acceleration yet. But it's a good guess. But I know you don't like me saying this. I never liked it the first time I heard it. There's something about this line is constant. That's the slope, right? But what is d over t? Speed. Now, so what is this a graph of? Now, you're not going to like that because your mouth says constant speed and your eye says something's going up and up and up. Yeah, the graph's going up and up and up, but the slope down here is the same as here. The ratio never changes. And so that, believe it or not, that is a graph of constant speed. I keep looking at it. Wait, it's important. So we're seeing it not just in the term, if you knew that d over t was s, you'd say, yeah, the slope is speed, and it's constant, isn't it?
Yeah.
All right, now look at the next one.
So,
Look at the next one. Whoa, what do you think this object's doing? So if I was in this car and I had a speedometer, and it would just stay at the same number, like 30 miles an hour, 30 miles an hour, 30 miles an hour. That's what this would show. But what about this trip? If I took this trip, what would be happening?
the speed decrease.
You want to take a guess on that?
It's accelerating and decelerating.
Okay, and I haven't used that word yet, but now we know that if we take the slope right here, the slope is the speed, right?
Yeah.
So here's a speed with that slope, and then I have a smaller speed, don't I?
Yeah.
I need to look at everybody's face, okay? You've never done this in any of your classes.
Not really.
That slope is speed. So right now the speed here is kind of high, and then the speed gets a little bit less, doesn't it? And then what happens? The speed gets a little less, and the speed gets a little less. And then what about here? Careful. What's the slope right there? What's the slope of a horizontal line? 0, isn't it?
Yeah.
So what's the
that's a
speed?
little bit over zero.
And then what happens? What the heck does that mean? What in the heck does that mean?
That means it's decreasing.
What now?
Goes in reverse.
It could be going in reverse. It could be, yes. All right, and then what about up here? Then, so we can actually look at this and say, you know what? This is not constant speed. And we're going to introduce a new word to you then. What happens if an object is not going at a constant speed? If it's slowing down or speeding up, there's a word called acceleration. Now, because humans like to name everything, all of these are acceleration, but mathematically what will happen is if it comes out to be a positive number, you'll be speeding up. If mathematically it comes out to be negative, it means you're slowing down. Humans like to call positive acceleration acceleration. What do they like to call negative acceleration? Deceleration. So if I ask you on a test, what's the acceleration, you can say negative 3 meters per second squared, and I know what you mean. You get it? Because the negative number simply means that I'm actually slowing down. So I know what it means, okay? And you will eventually know that. Okay, let's try this one. Let's try this graph. If you were in this car, what do you think? And that's today, we're thinking a lot today. Do you notice I changed something on you? I changed something, watch. Anytime you try to analyze a graph, you have to look at the axes, don't you? This is a distance and time graph. What was this one? See that? But look at this one, I changed it. What did I change?
Speed.
Speed and time.
Speed.
Okay, Ed? Everybody see that? Speed and time.
The net force is 0.
So that's it, I mean.
Okay, now, good question. Now, wait now, let's think about it. So, ready? At this time, you were going at 30 miles an hour, 30 miles an hour, 30 miles an hour, 30. Oh,
No acceleration.
that's right. This is also, wait a minute, I see. I could represent constant speed this way with a distance time graph, or what if I had a graph of speed and time? I could represent constant speed that way, couldn't I?
Yeah.
I keep looking at you because I don't want to lose you. As we get into acceleration, I know you think acceleration is easy. I can promise you it's not as easy as you think. Okay, now let's take a look at this one. This is interesting.
That is.
What's
Is that
this?
constant?
It's the same thing.
Okay, now some of you aren't paying attention because that's a repeat of this one. Okay, so with the book I got this out of, they wanted to show on panel 1 constant speed, panel 2 not constant speed, some kind of acceleration, deceleration. Then on panel 3, see how they're together? They wanted to show constant speed, but what's this one? Constant speed. Okay, now this one right here is tricky. This one's tricky. Okay? Now, we're going to get into acceleration today, and I'm going to come back. I'm going to come back to these graphs, okay? We're not ready for it right now. But we're going to talk about the word acceleration today in just a second. So let's go back to our original paper. All right, so what we have here is the speed equation, and then we looked at it mathematically. We also looked at it graphically. And what I would like you also to do is to think of it conceptually, and I'm going to draw these funny little dots here. And so I want to show you, I want you to pretend like you're in a car, and the car has an oil leak. And there's a little drop of oil comes out once a second. And they just made a brand new highway made out of concrete. And you're going to take your car and you're going to do something, and so let's say I go back after you leave and I look at the oil spots on the car, on the driveway. So here I see this, and I see, let's say I saw something like this. Now, the dots represent two things. What do you think the dots represent? If I took a part of your trip and I analyzed it, and I looked at your oil drop spills, what do you think the dots, tell me one thing the dot represents. Yes?
It represents constant speed.
I agree with you that this is constant speed, but how do you know that it's constant speed?
Because you said 1 oil drop a second. Well, if it were accelerating, the oil drops would be greater or lesser distances between.
Okay, now you're thinking conceptually, because if you're going at a constant speed, these dots represent time, don't they?
Yeah.
So between here and here is 1 second. So 1 second, 2 seconds, 3 seconds, 4, 5. Is that correct? But they represent something else. It's how much distance you traveled during that second. Now here's the hardest part for you. If you travel the same distance in the same amount of time, what's that called? What's that called? If you travel the same distance in the same amount of time, what's that called? Constant speed. Now, in just a minute, I'll show you where things don't travel at the same, they don't go the same distance in the same amount of time. You get it? And then we'll see that later. So one more time, we have the mathematics, plug and chug and get the math thing, okay? And then we have the graphic, looking at it graphically, and we look at it conceptually like this. Now, if you don't like the idea of oil drops, most physics books, I don't have a picture in here, but most physics books, sometimes they'll say this thing called a strobe light. Have you ever heard of a strobe light? If you're in a really dark room, and you can buy these at Walmart, and they're kind of cheap at Walmart, but if you want to buy a nice one, they're really nice. If you get a nice one that's a strobe light, is you can set it, and a bright light will come on and then go off. And it'll come on and go off. And you can set it. I want to go on and off once a second. I want to go off and on 10 times a second. 10 times a second. And so what happens is, if you're in a really dark room and it comes on once a second, here's what I see. Hey, I saw you. Oh, how'd you get over there? Because I didn't see you when the light was off. I didn't see you. So what I would say is, ba-boom, ba-boom, ba-boom. Now, what if I saw you like that? What if I saw you there, and then the same distance, then I knew you were moving at a constant speed. And so physics people actually will drop balls and things like that and roll balls on ramps, and they'll take these strobe lights. What happens every second? Where are you at every second? And sometimes they'll put these pictures on the same picture. They're called multiple images. Have you ever done, anybody photographers in here? You ever done like a double image where you have, okay. So they can actually keep the shutter open, and the strobe will go on, off, on, off. And so the ball's here, they have a picture of it, and then a second later it's here, and then, see that? And so that's how they get some really neat things. Now, I use the oil drop thing because I think people understand that also. All right, now, let's go over here, and in your book, let's take a look at this page right here. And there are some vocabulary words, and they're not hard. They're not hard. And I want to get to some of the harder stuff today. But one of these things is called instantaneous speed. Instantaneous speed. Okay. Now, when I drive my car, I can actually tell my instantaneous speed by looking at the speedometer. Is that correct? And what that tells me is in an instant. How fast am I going in an instant? Now, it is true that whoever made that it's hooked onto my wheels, and it actually is talking about rotation. It actually measures how much of a rotation every second, and it converts that into the needle moving up to 10 or 20. I'm not sure you guys even have cars. Your cars even do have needles on them anymore, or are they digital? You have needles? Okay, so whatever. Whether you do electronic or you have the digital read or the arm that comes across. Now, hang on. Now, the other thing that is on cars is called an odometer, and an odometer is for distance. I would say most, not all. I'd say most you have a car that has not only an odometer telling you the total number of miles your car has driven, but you also have what they call trip odometers. Now, trip odometers, sometimes you have a little button there, and you push it and hold it, and all of a sudden it goes, trip A, 00000, and it says, so you're ready to start a trip, you said, I'm going to push the odometer, and when we're going to the mountains, I'm going to figure out how many miles we're going to go. And when you get done, you look at it and say, oh, okay, I know how many miles it took for that trip. And I took that, if I want to cut that off, that goes back to the total life of the car odometer. You get that? All right. Now, the reason I need to tell you that is, what's the difference between instantaneous speed and average speed? And I know it doesn't sound like we need to have this in physics, but we do. Okay, so watch. Instantaneous speed, look at the speedometer needle. I get it. At an instant, what's your speed right now? You get that? Now, what's average speed? Did you know that I could find the average, if you go somewhere this weekend, let's say you're going to your grandma's house, and you could even try this yourself. You could actually find your average speed to grandma's house without ever looking at the speedometer. So you can find average speed, and I need two things. Tell me the two things I would need to do that. Since you already answered two questions, you answered one. Anybody else? I'll come back to you guys.
I got you.
All right,
The distance, the total distance,
that's from the odometer.
yeah, over the time it took to get there.
That's right. So I don't have to ever look at the speedometer needle to do average speed. Now, you might say, well, in physics class, is there ever a time that you need to do average speed? Yes. Because I want you to think about that trip. Think about the trip, okay? If you had a graph of the trip going to grandma's house, and you'd say, and you can bug the heck out of your dad or mom, whoever's driving. You're in the back seat, and you say, I'm going to bug the heck out of them and say, every minute, I'm going to ask them what my distance is. And then you have a graph, 1 minute. And you can do 5. If it's a long trip, don't do that. Do 10 minutes, whatever. So let's say you do 5 minutes. Every 5 minutes, tell me the odometer reading. Tell me odometer reading. Tell me again. And you could make a graph out of that, and it would be a profile of your trip. Now, guess what? Your trip would not look like this. Here's distance and time. Your trip would not look like that. Now, because what happened, I had to get started, didn't I? I had to get started. I was at 0 speed. Then my speed got higher and higher and higher, didn't it? Oh, stoplight. See? And so lots and lots of things could have happened to you on your trip. So what's the best speed you can give me if you know things are not going at a constant speed? If you're not going at a constant speed, what's the best speed I can give you? The average.
The average.
All right. Now, wait a minute. This is important. You don't think it's important? You're going to find out later that when objects fall, all right, you know what they're doing?
They're falling.
They're not going at a constant speed.
They're
They're
accelerating
going faster and faster. Now,
like a snowball.
if an object is going faster and faster and faster, and you say, what's your speed? Now, this is where it gets complicated, okay? If an object is accelerating, and you say, what's your speed? You said, I have many speeds. Yes. Yeah. You said, I have many speeds. So you couldn't ask me, hey, wait. If I'm accelerating, if I'm speeding up or slowing down, and you said, what's my speed? I can't tell you, you have many speeds, don't you? Now, I could give you the instantaneous speed. If I could freeze it in an instant, I say, 55, 58, 4, 50. I could give you an instantaneous speed, couldn't I? But sometimes when objects are falling, for example, we want to know, what was your average speed during that second? And what I need is total distance. What's the total distance you went? And what's the total time? Does everybody get that? And when would I use that? When I'm not going at a constant speed. If I'm going at a constant speed, I know the miles, I know the hours. You get it? Miles per hour. All right, you okay on that?
Yeah.
That was pretty easy. So we know the difference between instantaneous speed and average speed, right? Now, here's something that I think is very interesting. Okay, this is where physics really comes into play here. There's a difference between the words speed and velocity. Now, for example, if I say you're going at 30 miles per hour, and you said, okay, that's a speed, isn't it? But what if I said, hey, if you're going at 60 miles per hour and you hit my car, am I going to be killed?
Yes.
And you say, wait a minute, you're not giving enough information, because guess what? If I'm going at 60 miles an hour and you're going 60 miles an hour in opposite directions, I'm gonna be killed.
120's fine.
But if I'm going at 59 miles an hour this way, and you're going to 60 miles an hour this way, you can run into me, and I'm not gonna be killed. So speed is a scalar quantity, isn't it? Speed says, direction has nothing to do with it. So if I just say, a car's going down the road 30 miles an hour, and I have a problem you're supposed to do, does it really matter which direction they were going? Not in this case. But if I talk about where it does make a difference, then I have to use the word velocity. So velocity is a vector. That's the second vector you know of so far. What's the first vector you had we studied a lot of? Start with F. Force. Forces were vectors, didn't they? And you found out that when forces can be added, you have resultant vectors, things like that. So vectors are definitely in the physics world, and velocity is not the same as speed. Now, 30 miles an hour is a speed. 30 miles an hour in that direction is a velocity, and you say, well, you're just kind of splitting hairs. Not really. If I'm in a plane, and I have a map, and it says, if I can get my plane to go at 200 miles per hour, and the city's due north, okay, and it's 200 miles away, I'm going to get to that city in 1 hour, aren't I? I'm going 200 miles an hour. It's 200 miles north. I should get there in an hour. But here's the problem. What if there's a wind going this way at 20 miles an hour? Then I need to say, wait, my vector, let's think about my vector. What if I'm going 200 miles an hour that way, and that's a velocity, and the wind is what? What did I say, 20? Or more than that, say 20 or not? Okay. If I'm going, and the wind's going 20 miles an hour east, I'm not going to get to that city. My plane will not go north. My plane will end up doing what? The wings might stay this way. The wings might stay like that, but the plane itself will go like this. And I will miss the city. You get it? I'm going to miss the city. You say, well, how do pilots ever get to a city? They used to do it by hand. Now they have a computer. You get that? And they have GPS and all kind of stuff there. But even a pilot, if you get your pilot's license, if your GPS and things goes down, you're supposed to be by hand be able to do this. I need to ask Jonah about that. But here's what you would do. You would actually fly the plane that way. You would fly the plane that way. All right? And you would fly the plane that way. Okay? And then what would end up happening? You'll end up going in a straight line. So you actually point the plane that way, and you'll end up going right to your city. So I understand most of your life, you don't have to worry about vectors very much. If you become an engineer, you better know about vectors. You're going to build buildings and forces involved. Winds are involved. If you're a pilot, if you get on a plane and the pilot happens to be there and they say, hey, do you know about vectors? And they said, no, you better get off that plane. Of course, that'd be stupid for them to say that. There's no way you get a pilot's license without knowing about vectors. You get that? All right, now, here we go. The reason I need you to know that velocity is a vector is because there's another way that we can study speed in a straight line. The first one, speed in a straight line at a constant speed. That's uniform motion. Non-uniform motion means you're either speeding up or you're slowing down. Now, what do you call that when there's a change in your velocity? If there's a change in your velocity, what physics words means there's a change in velocity over time? What is that? Acceleration. Okay, so now here's the part that I think is interesting. There are 3 ways, if I'm driving a car, there are 3 ways that I can change, that I can accelerate. Tell me the 3 controls in a car that could accelerate my car. All right, raise your hand. Somebody hadn't answered one yet. All right.
Gas.
Right, the gas pedal, it can actually make me speed up. All right, next. What's another control on the car that makes me?
Oh.
Cruise control.
Cruise control.
That's throttle.
No, that would make me go to constant. That would make me go to constant speed.
Cruise control, you can up
No, you
those.
can use the.
You can use the dial to up.
Oh, okay.
So I guess there's 4.
All right, wait. All right, wait. All right, wait. I get it.
You can push it.
I get it. What's another one? Somebody else had an answer one. Colleen, you have your hand up.
Outside, start pushing it.
You press the brake.
Brake. The brake would actually make me accelerate.
Negative.
Hang on. It's negative acceleration, but it is causing a change in my velocity. And the one you're probably not thinking about, besides cruise control. What's that one?
Steering wheel.
How would that happen?
You,
Accelerates you that way.
what you do
Okay,
is
now,
you quickly turn.
wait now, this is important. Okay, this is important. Wait a minute. If you want to have a constant speed, all you have to do is make sure the speedometer needle reads the same number. You get that? You want constant speed? That's easy. Constant velocity is not easy. Constant velocity, you have to have a constant speed and, look at me, constant speed and a constant direction. If you're not going in a constant direction, because the velocity has direction, right?
Yeah.
If you change either the speed of that vector or the direction of that vector, you're accelerating.
So it's steering wheel.
So this is a great picture right here. Look at this picture right here. If a person's in the car and they're out in a big parking lot and it says 30 miles per hour, 30 miles an hour, 30 per hour, right, and you say, hey, does that person have constant speed?
Yes.
Yes. Do they have constant velocity? No. Now, let's take a look. Ready? Because at one time, their velocity was in that direction. And then their velocity was what?
In that direction.
And then their velocity was...
The other direction.
And remember, you're not going to like this because you think the only way to change your velocity is to change your speed. No, if you change your direction, you are accelerating. Now, what you're not going to like about this, and I didn't like it when I first learned it, was that if you change your velocity and that change is in the direction you're going, then you're going to speed up. If the change is in the opposite direction you're moving, you're going to slow down. But if the change is in direction, we end up getting a force that actually works this way. A force is created inwards. And so therefore, it doesn't actually make you go faster or slower. This car is accelerating right now. But you're not going to like that because you think the only way you can accelerate is to change your speed. He's not changing his speed. He's changed his direction constantly. This is actually constant acceleration. But because the direction of this vector here, this inward force, is not in the same direction you're going, I'm not going to make you speed up or slow down. Now, scientists understand that a force is created here, and they build things like they'll eventually build maybe a city in space. If they were to build a city in space, they would want to, and some of these movies you watch, do you ever want to see these movies where they're going all the way to Jupiter or something like that? There's always one part of the ship that's doing what? It's spinning, isn't it? And what's happening is they're causing an acceleration inwards. And that's going to be like artificial gravity. See that? If you go to the space station right now, it's not spinning. So every time you see those astronauts, what are they doing? They're going like that, right? But in your movies, they have a place where it's spinning and it's actually accelerating. The ship's going at the same speed, but there's acceleration because of that change in direction. You get that? And they can actually make artificial gravity like that. So if you're, and nowadays, all your movies have enough money, they can hire a physics professor to be their consultant. What do you think about that? No, they can't do that. Now, some directors will say, I know you can't do it with physics, but it's going to look great on the movies. And sometimes they just take their advice. It doesn't mean that everything in the movie is exact. You get that? And sometimes these physics people, they watch movies and they said, I'm going to write a letter. I'm gonna write them a letter, you know. You can't do that. And some people, they sometimes even know you can't do it, but they kind of thought it looked good in movies, all right? Okay, so now look over here, and you'll see what this page is about. It says acceleration is a change in, hang on. Look right here. It's a change in velocity over a change in time. Everybody get that? Now, the only reason, how do you find delta anything? Oh, I got it, one more minute. How do you find delta anything? Okay, look at me. When you did slope, delta y, delta x, it was always the second value minus the first. So in physics, how would you find the change in velocity? And the change in velocity would be and here's physics people putting name tags on here. It would be the final velocity minus the what? The initial. Now some physics people like to put an I for initial, and some physics like to put a 0 for original. And it depends on what physics book you're reading. You get that? So if you were going to try to find the change in velocity, it'd be the second velocity minus the first velocity. Everybody yes? And then change in time, and sometimes I just write time here because I think you understand it doesn't mean what time it is on the clock. It really means how much time went by. It's really change in time, right? All right, last thing, wait, 5 seconds, ready? What's that car doing? He's speeding up, it must be accelerating. Slowing down, must be accelerating. Wait a minute, you go over a hill?
Accelerate.
Roller coaster?
Accelerate.
Oh, that's why I feel that. Okay, all right, thank you very much.